My name is Jack Porter. I'm the Unreal Engine Mobile Team Lead and also the Engine Development and Support Team Lead here in Korea. I've been working on Fortnite Battle Royale, bringing it to mobile, and today we're going to talk about how we were able to optimize that and bring it to mobile. So I guess the correct title for this session should be One Game, All Platform, because that's the biggest problem we've had for bringing Fortnite Battle Royale to mobile. In the past, when people have ported mobile games, almost always there have been compromises made to the mobile version. For example, simplifying content, reducing the size of the level, reducing the number of players. So typically mobile ports end up being a reduced, cut down version of the real game. But for Fortnite, we set out to support cross-play across all platforms, and therefore the map has to be the same on all platforms, and anything that affects gameplay has to be the same for all platforms. Has been to use the scalability system and expand the scalability systems in Unreal Engine 4 so that we can use the same content and the same assets and have them running on all platforms. And one benefit of this approach is that the optimizations we've made for mobile are actually making low-end PC and console faster and helping optimize for those platforms as well. So this talk is going to be mostly about optimization, and I'm not going to cover all of the other things required to adapt the game to mobile. For example, being able to make good control schemes, or being able to have the player interact with doors and objects in the world in an easier way than they would have. For example, on a controller, on a console, you can press the A button to open a door or perform an action. Here we've got a touch screen, so we want to automate some of those features, some of those behaviors, so that the user, to adapt to the user's controls. So this is what Fortnite looks like in high quality mode on PC. We already had a low quality mode for low end, for medium and low end PCs, where we disable some of the rendering effects and we've changed some of the draw distances to the levels of detail, simplified some materials. Settings that are built into Unreal Engine, we can change, your game can define settings that are also affected by scalability groups. So we have a bunch of Fortnite specific scalability settings that we've made console variables for. And for example over here, the first few scalability settings for the view distance are defining game-specific view distance settings that don't make any sense for other games. Down the bottom, we have the engine-specific view distance multipliers and those kind of things. But using this one system allows us to tweak engine parameters as well as game parameters with a single number for each of those different groups. So now we have to decide which scalability group we want to use on which devices. We do that using device profiles. So at the game startup, it looks at on Android and on iOS. We look at what kind of phone we're running on, and we have a bunch of profiles, and we choose the most appropriate one for that device. And then that device profile can set any console variables it likes, including scalability settings, or it can also override the default settings for the engine. Probably a bit small to see, but this is, over here is the iPhone 10 device profile setting, and these are the console variables that are getting set for iPhone 10. And then that's based, the first line says that it's based on the iOS 5 scalability device profile, which is where we set all the scalability groups to 2. So in the previous slide, when we were talking about At fully scalability level 2, these are what the parameters are for the culling and the density. Those are going to be automatically enabled based on the fact that we have enabled the scalability group here. This is based on the iOS device profile, which sets some default parameters for iOS, and that in turn is based on the mobile, which is shared between iOS and Android. So this gives us a way we can define settings for performance and scalability on groups of devices without having to worry about individual devices or a huge amount of detail. Apart from performance, we also have a different axis for scalability, which is memory. And it doesn't always correlate with performance. A lot of Android phones have a lot of memory, but relatively low power in terms of GPU. Whereas an iPhone 8, which has a very fast GPU relative to other phones, has only 2 gigabytes of memory. So we have this different axis. We decide, we call them they're our memory scalability buckets. For low, medium, and high, we can group our devices into those, and then we can make different decisions for memory kind of settings. So when we started, the game was built for PC and console, and this was a major effort. We started to see how well it would run, so we tried to load up the content on a 4 gigabyte device, like an iPad Pro, which was the largest, fastest device we had. And we quickly ran out of memory. So on iOS, we found we need to reserve, or we need to allow, or we can allow ourselves about 700 megabytes for every 1 gigabyte of memory on the device. So most iPhones that we support have only 2 gigabytes of memory, and so we try to fit our game and all its content in 1.4 gigabytes, and so on for 3 gigabyte and 4 gigabyte devices going up to the largest iPads. On Android, the situation is a lot more complicated. So you typically have more memory on Android devices, but there's a lot more going on. There's the Java virtual machine. There's often a lot more background processes on Android because it's a much more open system than iOS. We can't necessarily, we cannot use the same values that we use for iOS. We found if you want to fit on a 2 gig device, your game really has to be less than about 500 megabytes, or the operating system will decide that you might be using too much memory and it will kick your application out your game. So we don't fit into 2 gigabyte Android devices at the moment. We do fit on 3 gigabyte devices, and we use the settings from 2 gigabyte iPhone for that. So about 1.4 gigabytes allocated to Fortnite for a 3 gigabyte Android device. It's also quite difficult to get accurate numbers out of Android because a lot of the memory is allocated either by the GPU that you don't easily get access to seeing the allocations, or the numbers you get are shared, and therefore they're not really telling you the full story about how much memory your application is using. So for memory optimizations, the biggest thing we did was to divide our Fortnite game into streaming levels. And in Fortnite, you start off skydiving from a bus. And when you start skydiving, you're seeing proxy representations of all of the objects. You're not seeing real objects. And as you get lower to the ground, we start to stream in the area around where you're going to land. So as you walk through the level, we're constantly streaming in and out content using the standard Unreal streaming level system. We made some engine level improvements. We have a lot of string data in our game. They were using 4 bytes on Android and iOS. We reduced that back to 2 bytes like other platforms. There are also a lot of engine level optimization where we have removed parts of some data from the data structures that was not strictly needed at runtime. We use ASTC texture format, and this is a great format because you can tune the size and the quality. So we try to keep the size as small as possible, and then we adjusted the streaming memory pool for texture streaming. Of course, there were content optimizations where we looked at textures that were allocated and decided, this is too much memory for a particular object. On the mesh side, static meshes and skeletal meshes, because we're sharing the assets with PC and consoles, we decided that we were going to get rid of the top level LOD and never use those LODs on Moodle at all. And so at cook time, we can now exclude that data and not use it at all. We also have a bunch of meshes that are tagged as being high detail, so some very non-gameplay important extra clutter meshes. If they're tagged by low detail mode, then we can remove them from Moodle at cooking time as well. Also, we don't load the grass and foliage data on very low memory devices. Those devices don't show any grass. And we can save both the content for the mesh as well as the data we use to work out where to place all of the foliage. And of course, there was a lot of content optimization looking at individual meshes and working out how to make it a suitable size that was going to work for Moodle when looking at the different LODs. For materials, we don't use anything except the lowest quality material settings. So a lot of our materials already had quality level switches in them, and we disabled, we removed all except the low quality variants when we're cooking for mobile. And we also disabled the permutations we don't use, such as static lighting. So there's now a bunch of settings in project settings which you can enable different lighting features. By disabling the ones you don't use, you can free a lot of shaded memory. Of course, we did, for audio, we did some downsampling and compression, but we also reduced the number of variations. So, number of different footstep sounds, number of different gunshot sounds, number of different heat effect sounds. We reduced the variations on all of those using, again, quality level switches. We have a quality node in the audio system as well. And we had some game-specific changes we made to save memory, which is to exclude a lot of the content which is used only by a single player, which is not supported on Moodle. And also, Fortnite is a free-to-play game, so we need to have a lot of cosmetic items, player skins, and different weapon models. And instead of preloading those, we work out which ones are needed in the game and stream only those ones. A big optimization was to look at our collision. We use per polygon collision for complex, for static meshes. The complex per polygon collision is used when, for example, when you're doing a hit trace or firing a weapon. And in many cases, we are able to use, we can either disable the complex collision if the object is a wall, even if the wall has a very slight 3D features. Depending on what those features are, we may not require them for weapon accuracy. The other option, or the other thing we did was to use lower LODs for collision. So in this case, in the screenshot, we used the second LOD was a pretty good good enough representation for the collision. We need to use the same collision representation on all platforms, so these changes also affected console and PC. Otherwise, we'd have situations during crossplay where different clients disagreed on collision, which would be bad. as I said about audio, so the left-hand side is how we used to choose variations for audio. And these are a whole lot of different impact sounds when the player got hit. So we had 12 of them. And it would choose, there's a random, this node here is a random node, and it would just choose one of those randomly. For mobile, we've added a bunch of poly-level nodes to reduce that variation. So we mix a few variations per platform, and then the quality node allows us to select between those. And there's a bunch of settings per platform which allow us to choose the different compression and resampling settings, which will allow us to reduce memory on particular devices. One other thing we changed is the real-time decompression threshold. So we store on the memory on the device, on the flash storage, we store all of the audio compressed, and then we could either decompress it after loading it, or we could decompress it when we need to play it. If we decompress it at playtime, there's a little bit more latency because the decompression has to start, and there's also some increased CPU, so there's a bit of a trade-off there, but depending on the kind of audio, whether or not we wanted to use decompress or not. Oh, so decompress at load time or not. So when we started optimizing Fortnite, we thought, oh, we just want the best visual quality we can at 30 frames per second. That's what we tried first, but then quickly we realized that if you start to render this mobile game at 30 frames per second with the highest quality, it's going to generate a lot of heat from the CPU and GPU working at 100%. And when mobile devices get hot, they reduce the clock rate, as well as being uncomfortable to play. So instead of that, our choice was to try and target 60 frames per second. And in fact, all the iOS devices are capable of running Fortnite mobile at 60 frames per second for just the environment. And we thought logging the frame rate, having the frame rate to 30 frames per second will give the device half the time to rest, and it gives us a little bit of a buffer for things like a very intense firefight with lots of players in the same area. So after we set this target, we want to track these as we're developing. So we made this every day. Our QA team would dump out these stats from a system we call Profile Go, which just goes to some different locations around the map. And it attempts to, or it measures the performance for maybe 20 seconds and then moves on to the next location. We're interested in the rendering performance here. So this is where we started. And you can see, we've got, over here is the draw calls column. This one here is the draw calls column. We've got 2,000 to 3,000 draw calls, and the frame time, we want to render at 30 frames per second. It needs to be less than 33. These are huge numbers. So we obviously had a long way to go. So after we identified the performance regressions, we ended up with much more acceptable numbers, but this kind of system allows us to track changes over time. So if we suddenly find we're slower, we can work out who's changed some content in a particular location, or maybe there's a regression across the board. And it lets us try things. For example, we can say to our artists, we think trees are expensive, can you try reducing the polygons by 20%? And they come back, we get a build, and we can run the Profile Go and compare it to the previous days, which is the number in parentheses. We also captured statistics during our playtests to identify particular targets. One of the important ones is the number of features per minute. So this is how many times in a minute the player is going to experience a big stutter in the game. And that was, apart from frame rate, that was our other key metric we tried to optimize for. This is from a tool called FramePro. FramePro is it's an API-based statistics, frame statistics program that's cross-platform. And we integrated that with Unreal Engine so that we could record very long playtests, and then the markers that we already have for our statistics system would allow us to evaluate and view for an entire gameplay session. We can pinpoint the areas that are not performing well. So in this case, we've 157 milliseconds was spent streaming a level in, and all the on-level streamed in pullback was executed. So we went to the programmer responsible and asked them what they could do about that. And it turned out the code in there was waiting for the rendering thread, and we just needed to remove that wait or rearrange the code a little bit. So, of course, mobile devices are multi-core devices. We've usually got 2 cores on iOS, and we usually have at least 4 cores on Android. The cores are not always equal, so on Android you've often got 2 big cores and 2 little cores, or maybe 4 big cores and 4 little cores. The little cores are very power efficient, but very low performance. On iOS, on 2-core devices, we ended up just using the existing system we have in Unreal Engine, which is the game thread and the rendering thread as our 2 main threads. And then we added an extra general purpose async task thread for stuff like streaming or physics. But on higher-end devices such as the iPhone 8 and iPhone 10, we have 2 fast cores and 4 low-power efficient cores. So we added a bunch more task threads for animation updates and particle simulation, physics, streaming for textures and streaming for the environment. So hopefully we're going to have those threads waiting most of the time. Like you can see here, most of the time they're waiting, and then they'll wake up to perform a few tasks and then go back to waiting. Early on in the frame, you can see animation and physics, which is this stuff here. We have to work out what animation pose we have everything in before we can render it. And then later on in the frame, we see some rendering tasks occurring. We found that in terms of generating heat, the CPU is much more important than the GPU. So it's really important for us to try and minimize any CPU work. In fact, the GPU is very easy to optimize for because you can simply reduce the resolution until you have something that looks acceptable and performs well. But there's not very much you can do to scale your CPU except by modifying your code. So it's very important for us to minimize that, and that's why we try to have all of those threads sleeping so that we don't generate much heat. On Android, as I said, we usually have more cores. We have at least 2 big cores and 2 little cores, but on more modern devices we usually have 4 big and 4 little. And the biggest performance problem, or the biggest use of CPU time on Android, we found was executing OpenGL commands. So unlike iOS, where we've got Metal on most Android devices, we're using OpenGL. Although we're currently working on Vulkan as well, we're evaluating if we can make that faster. For OpenGL, the driver has a lot of overhead because there's a lot of state and a lot of management that has to happen in the driver. So instead of having Unreal's render thread do a lot of work in Unreal to work out what to render and then issue OpenGL calls, if we separate those 2 things, so here the top one's the game thread, And then the second one here is the rendering thread, which is working out what objects we need to draw and how they need to be drawn. And then this third thread here is the thread that is used for issuing OpenGL calls. And you can see that thread is the one that is taking most of the performance most of the time. So giving the whole 33 milliseconds to the RHI thread allows OpenGL, the OpenGL driver, to that time to be covered by us doing other work in other threads. On the CPU side, as I said, CPU is our biggest problem. The amount of time spent working out what you need to render scales by the size of, or the amount of objects you have in the environment. So culling and calculating the relevance is one of the largest parts of that, which does scale to the size or the number of meshes in the world. Using level streaming allows us to get rid of large amounts of objects from the world when we don't need them, when they're not near the player. But our biggest problem is draw calls by far. And more than just the call to draw index primitive, which is a little bit expensive, the state setup, so changing the shaders, setting shader parameters, setting uniform buffers, is very much more expensive on a mobile device than it is on PC and console. So on console we have about 3,500 draw calls per frame. PC has more than 4,500, and on mobile we can't afford anywhere near that. In this table, we are limiting ourselves to around 1,000 draw calls in the most complicated case. This is City Overlook, which is on a hill overlooking the Tilted Towers section of the map, which has got a lot of buildings. Each of those buildings is destructible, and so they cannot easily be combined into a single object that is rendered once, so they need to be separate draw calls. And on Android, this is our biggest issue still. You can see the cost of the draw calls is much more expensive at the moment. We're working on that, and there's more work to be done. It's one of the optimization efforts that's ongoing with Android. We find, as I said, we find all of the CPU time is spent in the OpenGL driver because we have this parallel rendering thread which can do engine work. So what to do about draw calls? I'd love to do aggressive distance culling, so just bring in the draw distance for everything, but you can't cull anything that will affect gameplay. So anything in the engagement distance, a few hundred meters, cannot ever be culled because the player could be trying to hide behind it. We can cull a lot of the decorative objects that don't impact gameplay. But one of the biggest benefits, biggest improvements was to use occlusion culling, which did not previously work on mobile. Another item I'll talk about after occlusion culling is the hierarchical LED system we used. So for occlusion culling, you need some data in your depth buffer so that you can test whether or not you render the depth buffer, and then you render some test cubes in that, and we get an answer back from the GPU as to whether or not any of that cube was visible. But we need a depth buffer for that, and on mobile we don't have a pre-pass, so the depth buffer is not available until the end of the frame. So this adds one extra frame of latency, and you do see a little bit more pop-in than you see on other platforms on mobile. And the RHI thread, because the render thread and the OpenGL calls are decoupled from each other, that is actually one more frame of latency on Android. There were some driver bugs and limitations on mobile devices that we had to work around. On particular Android devices, we were seeing some some of them had limits to the number of inclusion queries that were available, and if we tried to use more of that, the whole pipeline would stall and things would get very slow. So we've had to add our own management layer in to virtualize the inclusion queries for Android. So when you're skydiving, you've got a really long view distance, and obviously you don't want to render those as individual objects. So we merge these, we merge many objects together with our hierarchical level of detail system, using both our new internal tools as well as Simplygon, and we generate these proxy meshes. And in this scene, in this state, there's no detail meshes are loaded, so only the proxy LODs are loaded. And as you get closer to the ground, it would begin to stream in the real meshes. So it's great for this case, but we can't use them at runtime. We can't use them in gameplay time because we can't change the distance for engagement. So this is what the raw geometry looks like in the City of Tilted Towers area. And if we just show the hierarchical LODs, these proxies are pretty terrible. They're only really suitable for skydiving. They're not suitable for any kind of gameplay. You saw that while you're playing. It would be pretty terrible. So we decided we needed to add one more. Another problem is that these meshes are static. So if the player starts to destroy some of the environment, given Fortnite is a destructible game, then you wouldn't be able to see that destruction reflected in the proxy mesh. So we needed to use our hierarchical LOD system to insert one more level in the hierarchy, which we call destructible HLOD. And we create this by merging the lowest level of detail for all of our individual meshes and atlasing all their textures together. And to support destruction, every object that was used to create the destructible HLOD mesh, all of those objects have an ID, and we store that ID in the vertex color. And then later, when we render that object, we have a texture we use as a lookup to see if a particular sub-object of that should be destroyed. And if it should be destroyed, we hide that section of the mesh in the vertex shader. So this is what Tilted Towers looks like, only using the destructible HLODs. And this is what it looks like using the full details of the mesh. So you can see there's a little bit of difference. For example, the trim around the windows has been removed. Everything looks a little bit lower detail. So now we have the system, we can choose a point where we want to stop using real objects and start using the proxy objects and have a much better representation. So this is how we shipped, which is the distant buildings, when you're on top of the hill, here the nearby buildings are rendering as real objects, but the more distant buildings, more than 50 meters away, are being rendered using the destructible HLODs. GPU is the easiest thing to adjust with the scalability settings. The kind of things that affect the GPU performance are the resolution, the shadows, the amount of foliage you have, and the quality of the materials generated, the shaders generated by the material system. There's also some pretty cheap things we can turn on or off, such as anisotropic filtering. If we turn those off, we get a bit of a boost in texture sampling. And we can also change the resolution of the landscape in the distance. So for resolution, as I said earlier today, the back buffer resolution is what we render the user interface at. And we have a separate adjustment we can make for the 3D scene. We try not to use that. We try just to scale the back buffer because there's some cost to the upscale which we wanted to avoid. And so we tried to render the 3D at the same resolution as the user interface where possible. And that was possible on pretty much all our phones except the iPhone 6s. For iOS, we choose this per device. For Android, we're doing it for large groups of devices with similar GPUs. The scalability settings for grass and for foliage have the ability to scale the density as well as the culling distance. So for low memory devices, as I said, we completely exclude all of the foliage completely. On all devices, we don't have the foliage cast any shadows. It's another quite big optimization. It can receive shadows from other objects like the trees, but it's not casting any shadows itself. As I said in my talk earlier today, material quality levels and feature level switches were used to adjust the content. On Android and iOS, we only ship the low quality materials. And this allowed the artist to remove vertex animation from the foliage or extra special effects that were not really necessary. We can also simplify the pixel cost for those materials by having fewer textures being sampled, for example. For shadows, the dynamic shadows had a huge impact on both the GPU and the CPU performance. So for a GPU, we have to render a bunch of objects to some shadow buffers, and for CPU, we have to traverse the scene and work out which objects we want to render shadows for and render them. So scalability for shadows involved reducing the resolution of the shadow map, the number of cascades. So on high-end phones we're doing 2, and on low-end phones we're doing 1 cascade, as well as the thresholds for object size. So on our lowest detail setting for shadow scalability, we have no shadows at all. For mid, we have a single cascade, and the minimum object we want to render a shadow for is something about the size of a building. For the high, we have 2 shadow cascades with an extended distance, as well as using smaller objects to be rendered into our shadow buffer. So there are a huge number of mobile improvements that are going to be available to you guys in 420. The minimum LOD for static and skeletal meshes, as well as the ability to remove those at cool time so they don't take any memory. The hardware occlusion implementation is available to you guys, as well as the RHI thread. There's ongoing optimization work for that, but the initial version of that is in 420. The HLOD tools and the workflow are in early access and in 420, as well as the audio quality node and the variation culling per platform downsampling and compression. We recently, in 419, in the screenshots you've seen up until now, we had a mobile lighting model that was not a very good match for PC. We've tweaked that shading model since these screenshots were taken to make it a lot closer. So it's a lot less dark than it is now. It's now much closer to PC. Something we've heard a lot of people ask for as well. As well as fixing up reflection capture brightness. There are a bunch of small bugs there. As I mentioned this morning, landscape now supports more than 4 layers, and pixelation has much reduced triangle counts. And on the memory front, we have 2 byte strings on iOS and Android, so there's no memory cost. Or a reduced memory cost. And there's no memory cost for unused LODs on for skeletal meshes and static meshes, or the grass has been excluded. These settings can now be adjusted on device memory. This used to be possible. And there's a bunch of engine level tweaks to reduce the memory usage for the material system. So as you can see, we've done a lot of work for mobile. There's more going on for Android especially. But using these changes, we were able to get Fortnite Battle Royale to run 60 frames per second on our target devices, and then clamping at 30 frames per second, we were able to have a continuous gameplay experience without overheating your phone or using too much battery. So thank you very much. If you have any questions, I'd be very happy to take